All right, happy Tuesday, everybody. Looks like a few of you are still joining us. Thank you all for joining the session today. We'll get started in just a couple minutes. First, just let me share a couple of announcements with you. All attendees will be muted during the presentation. If you do have questions, please type those into the Q&A or the chat box, and then we will do a little Q&A session at the end of the presentation. All right, now it's my pleasure to introduce our speaker for today, Azunna Sunday Ugochukwu. Azunna is a professional in the field of civil engineering with a focus on structural engineering. Born in Abia State, Nigeria, he has pursued his academic and professional career with determination and excellence. He has demonstrated his expertise through various research publications on sustainable engineering and successful project executions, contributing significantly to the advancement of engineering practices. He holds a Master of Structural Engineering and a bachelor's degree in civil engineering, as well as an advanced diploma in civil engineering technology. He is currently running a Doctor of Philosophy program in structural engineering in Universiti Putra, Malaysia. Today, he will be presenting a session titled A Review on the Material and Structural Characteristics of Geopolymer Concrete. All right, the floor is yours. Take it away.
Okay. Good afternoon, everyone in the US. It's quite about AM in my location at the moment. So it's my pleasure to present to you today a review topic on geopolymer concrete. So a lot has been done on geopolymer concrete. I'll try to run through some of the mechanical properties and the material properties so far that has been discussed and analyzed in the field of geopolymer, because it's quite new. It's not that vast yet. But the world of concrete is going towards a more sustainable and a more environmentally friendly concrete. So geopolymer concrete is on the rise, and knowledge acquisition in this aspect of civil engineering is increasing day by day. So some of the things we'll be going through today, I'll run you through geopolymer, what geopolymer concrete is. We'll paraphrase through the material characteristics, what constitutes geopolymer concrete. This is where I'll be focusing on the conversation today, mainly on the material properties, because that is where there are lots of problems and lots of questions in geopolymer concrete. Then after that, we'll touch a bit into the structural properties, how geopolymer structural elements perform in terms of strength, durability, flexion, and all that. Then we'll check some of the design codes for Eurocode, for American standards, how they apply in the design of geopolymer elements. So why are we talking about geopolymer concrete today? We all see global warming is on the rise. The ozone layer is being destroyed. I think recently this year we heard of the flood in Spain, Valencia precisely, that claimed a lot of lives and properties. So the damage is basically due to the production or emission of carbon dioxide. And we know that the production of cement contributes a key part to the emission of CO2 into the atmosphere. And it's estimated that by 2050, this emission will reach about 4.38 tons. So it's high time we start thinking about moving away a bit from production of normal ordinary Portland cement and beginning to embrace geopolymer concrete. I started here so that we know the importance and the emphasis on geopolymer concrete today. So it's not something to be taken lightly. In most advanced concrete in Europe and in Asia, a lot of funds have been pumped into geopolymer concrete so that it can become a reality in the near future. So before I go further, I'd like to know how many people have done geopolymer concrete, or you have an idea or any experience whatsoever, just by maybe a raise of hand. Yeah, I can see.
Looks like one person has raised their hand.
Just one. Okay, that means virtually everybody is new to geopolymer. Okay, I asked because so that it will help me to know my audience and the people I'm communicating with, because of the terms I am going to be using. Now, there are two basic things in geopolymer concrete. It's called the alkaline aluminosilicate precursor, or you can call it the solid precursor, or in simple term, you can call it a binder. So that binder exists in natural form, and it also exists in as a byproduct. In the natural form, we have clay, we have mud. Then some of the byproducts are fly ash, slug, and silica fume. So the major constituent of these precursors is that they have calcium, they have aluminum, they have iron, and they have magnesium. So what determines their material property to be used as a precursor is the chemical combination of the binder. So I'm going to be calling it binder in simple terms so that you understand it much better. But the ideal name is aluminosilicate precursor. Then after that, the next major thing in geopolymer concrete is the alkaline activator solution. So you can simply call it the alkaline solution. Now, how is this alkaline solution produced? It's a combination of sodium hydroxide or potassium hydroxide and sodium silicate. So if you want to, say, produce geopolymer concrete, after you've done your mix design, you get the weight of your precursor or your binder per se, combined with this your alkaline activator solution, which is sodium silicate or sodium hydroxide. So when you combine them, the way you combine them is these binders have silicon oxide, calcium oxide, iron oxide, and aluminum oxide. Now, the alkaline solution helps to extract this chemical composition in the compounds, which enables them to exhibit cement properties. So it's the combination of these two that enables your concrete to bond. It's what determines the strength or the durability or the structural performance of the geopolymer concrete. So basically, this is the summary or the start of what geopolymer is about. So I'm going to go more into details about the alkaline precursor, and later I'll talk about the precursor and the alkaline solution. So the major ones that I'm going to be focusing on, which is mainly used for geopolymer concrete all over the world, is fly ash and GGBS, that is the slag, ground granulated blast furnace slag. So the fly ash is divided into two categories. We have the class F fly ash and the class C fly ash. So what determines these precursors, like I said, is the chemical composition. So if you look at class F fly ash, the composition of calcium hydroxide is low, just about 1.2%. While in class C fly ash, the composition of calcium hydroxide is about 14.5%. Now, the difference is class C fly ash has a percentage of calcium hydroxide that is above 10%. That is how you know a class C fly ash. Its calcium hydroxide is above 10%, while that of class F is below 10%. Then the calcium oxide content of the slag is above 40% most of the time, 40% up to 60%, even 65%. Then the silicon oxide in class F fly ash is very, very high, more than 60%. It's the highest in all the binders. Then that of the slag, the GGBS, is the lowest. Now, a key understanding of this chemical composition is what is going to determine your mix design. You have to understand the chemical composition of your binders before you know the ratio in which you're going to use them in the design of your geopolymer concrete. Now, I want to break it down in a layman's language because geopolymer concrete has a lot of chemistry in it, but I'll not go too deep into that. So what you will just know is the calcium oxide takes care of early setting. Now, any binder that has a high percentage of calcium oxide has a tendency of giving you a very high early strength. So after 3 hours, after 4 hours, after 1 day, you can get a very, very high strength. Then the silicon oxide gives you a high strength also, but it takes a longer duration. So now take, for instance, I produce my geopolymer concrete with class F fly ash. There's a tendency that at 3 days or at 7 days, I will not get a very good strength. If I design for, say, 40 MPa, on the 3rd day, I may get less than 10 MPa because it takes long, and I may not even get up to 40, up to my design strength. Then take, for instance, that I use slag or class C fly ash. So if I design, if I produce a geopolymer concrete with class C fly ash, in the next 1 hour, I can get up to more than 70% of my design strength. So these are the basic things I want you to bear in mind here because I'm going to be discussing about it later on. It's going to determine everything we do in the future. So now there is a negative advantage. There are 2 basic challenges with geopolymer concrete at the moment. 2 basic challenges. Number 1, because the good part of geopolymer is that it has advanced mechanical properties more than normal concrete. The compressive strength is way higher than normal concrete. The flexural strength is way higher than normal concrete. The bonding characteristics is way higher than normal concrete. So let's say I design a geopolymer concrete for 30 MPa, and I design a normal concrete for 30 MPa. The normal concrete can give me, say, 40 at 28 days. The geopolymer concrete can give me up to 70 at 28 days. So its mechanical properties is it's awesome. Its mechanical properties are very, very advanced. Now, the disadvantage of geopolymer concrete is that it sets very, 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 very fast. The setting time is very fast, which is what has made the concrete to not be very practical. The setting time in some cases is even less than 10 minutes. So you understand that more in the long run. That setting time is more of a problem when you use class C fly ash or the slag or the GGBS, because the composition of the calcium oxide in class C fly ash and GGBS is very high. So it accelerates the setting time of the concrete. So that being said, I will now go into the alkaline activator solution or the alkaline solution. So like I said earlier, it's a combination of sodium hydroxide and sodium silicate. So the sodium hydroxide is prepared by dissolving, the sodium hydroxide solution is prepared by dissolving pellets. This what you see there, the white pellets, it's sodium hydroxide. That is how you buy it. That is how it's supplied from the company. So you prepare the solution by dissolving these pellets in water. So what determines the quantity you use is dependent on the molarity of sodium hydroxide you want to use in producing your concrete. Normally, we have from 6 mole to 20 mole. Can use a molarity is prepared by dissolving 40 grams of these pellets into 1 liter of water. That is how you calculate the molarity. Now, when you dissolve it, it releases a lot of heat. The solution becomes very, very hot, and it can even damage your hand or the skin. So most times when you want to prepare, when you want to cast, you prepare your sodium hydroxide 24 hours prior to your casting to enable it to cool down and enable you to cast your concrete. Then the sodium silicate is supplied in a container like this from the company. So normally the ideal design, in the normal design of geopolymer concrete, you don't use water. This alkaline activator solution is the liquid part of your geopolymer concrete. Your sodium hydroxide solution is expected to have a certain amount of water. If you use, say, 8 mole, if you're preparing 8 mole of sodium hydroxide, that would be like 26% or thereabout of the total solution. So you have about 74% of water. Then the sodium silicate also has a certain percentage of water, but it's determined from the factory. Most times it's around 36 to 45% of water, depending on how they produced it. So the water in the sodium silicate and the water in your sodium hydroxide is what is ideally meant to be the water that you will use to cast your geopolymer concrete. Now, the two basic functions they do is your sodium hydroxide takes care of the hardening, the solidification of your concrete. It gives you the strength. It helps the concrete to solidify. The sodium silicate helps to make your concrete more dense. It gives you a more compact structure. It works on the microstructure of your concrete. So it gives you a higher bond. So now on a quick run, sodium hydroxide accelerates the setting time of your geopolymer concrete. So the two basic things that affect the setting of your geopolymer concrete is the content of the calcium oxide in your binder and the molarity of your sodium hydroxide. That is what affects the setting time. It shortens the setting time actually. So if you use a molarity of, say, 20 mole, your setting time is going to be very, very short because the water content will be very small, and then the reaction is going to happen much faster. So even in less than 5 minutes, your concrete could become solid. So that is why you're not advised to use a molarity of sodium hydroxide that is too high. So then we'll now go proper into the parameters that affect the design of your geopolymer concrete. So if you want to start with, I'm going to start with the workability. Now I kind of compressed it here. The workability and the flowability is almost the same thing for geopolymer, and the setting time. These parameters are directly proportional to each other. So I'm going to begin with the alkaline solution to binder ratio. So the alkaline solution to binder ratio is similar to water cement ratio in normal concrete. So from the chart here for the alkaline solution to binder ratio, you can see that the workability increases as the ratio increases. So what it means is, as you increase the alkaline to binder ratio, it's like you're increasing the water content of your concrete, and you're reducing the content of your binder. So if you want to have a geopolymer concrete that is very high, that the workability is very high, that is going to flow very well, you're going to have to use an alkaline solution to binder ratio that is high. But normally, the accepted alkaline to binder ratio is in the range of 0.35 to 0.6. Some literatures use up to 0.8, but normally you don't get up to 0.85. This is too high. It will be too watery and the strength will be almost zero. So why do I say it's related to the setting time? If your concrete is more workable, it means the water content in your concrete is higher. It means the alkalinity in your geopolymer concrete is less, and it means it will take less time to harden, to solidify. So you have a longer duration to cast it. Then the next thing is the molarity of the sodium hydroxide. So the molarity, like I said, it starts from mostly 6 mole, 8 mole, 10 mole, 12, 14, 16, 18, and 20. But most times, if you're doing design of a geopolymer concrete, you're advised to limit your design to 8 mole and 14 mole most of the time, depending on when you get very advanced in the design. So if you look at the chart, you can see that the workability reduces with increase in molarity. So like I said, the molarity means the sodium hydroxide is what propels solidification of your concrete. The sodium hydroxide has this hydrogen hydrates that reacts, that helps in dissolving the calcium hydroxide in your binder, that helps in dissolving the silicon oxide in your binder, that helps in dissolving the aluminum oxide in your binder. So if you use a less molarity, it means the hydrates of your oxide is not much. So your geopolymerization will not happen very fast. It may take longer. So you have a high strength of having a high workability when your molarity is small. However, as the molarity increases, you're increasing the hydrates in your sodium hydroxide, which means the geopolymer reaction is going to happen faster, and your solidification, the solidification of the concrete is going to happen also very fast. So you have a lesser time to cast your concrete, because it will solidify very fast. It will not be so watery to enable casting. Then another factor is the ratio of the sodium silicate to sodium hydroxide. So like I said, your alkaline liquid is a combination of your sodium silicate and your sodium hydroxide. Now, how do you know the ratio to combine both of them so that it will give you the desired properties that you want in your concrete? The ratio is also in the range of 0.5 to 2.5. So like I said, the presentation is a literature review, and I attached all the literatures at the end. So if you want to get more knowledge on this parameter, you check through these literatures. They will give you more information about it. So it's in the range, like I said, it's in the range of 0.5 to 2.5. So now you can see that your workability reduces with an increase in the ratio of sodium silicate to sodium hydroxide. Now, normally, your sodium silicate is thick. It's a very thick liquid. And your sodium hydroxide is more watery. So if you're increasing the ratio of sodium silicate to sodium hydroxide, it means you're increasing the quantity of sodium silicate in your geopolymer concrete. Now, the viscosity of sodium silicate is way higher than that of water. So it will make your concrete to be more sticky. The concrete will be sticky. It will not be so watery anymore. So if you want, if the purpose of your concrete is a concrete that requires a high workability, you have to reduce the quantity of sodium silicate in the mix. That is the summary of what this means. Then another factor that affects the workability, like I said, is the calcium content, the calcium oxide in the binder. So if you look at the third part, where I indicated the slump and the binder type. So if you see the first chart there is about 155 mm, which is the highest slump. That one is 100% fly ash. There's no GGBS in it. So the workability is high because if you remember, the chemical composition of fly ash has a very small, it's a very small percentage of calcium oxide. So because of that, it takes longer to set. So that's the major reason why you see the workability is high. However, when you introduce the slag into your binder, it means you're increasing the calcium hydroxide content in the binder because GGBS has a higher percentage of calcium oxide. So that is the major thing that reduces the workability because it sets very fast. So as you mix, it accelerates the solidification. Geopolymerization begins to take place instantly. So that is what essentially it means. So if we are designing a concrete with high workability, if we want the workability to be high, we have to use a high alkaline to binder ratio. We have to use a molarity that is not very high. Also, the ratio of sodium silicate to sodium hydroxide has to be low. Then you have to use a binder with less calcium oxide in it. Then I'll now go to the compressive strength and the factors that affect compressive strength. Okay, now one of the major factors that affects compressive strength, not just compressive strength, for strength of concrete, is the calcium silicate hydrate in that concrete. So what it means is you need a percentage of calcium in your binder. You need a percentage of silicate also in your binder. So if you look at it, you see that most times, if you use only fly ash, because the calcium oxide in fly ash is very low, you're not likely to get a very high strength. At the same time, you can get a very high strength with GGBS if you use slag, because it has high percentage of calcium oxide. But it sets very fast, like I said. That's the negative part of GGBS. And the setting very fast also leads to flash setting. It causes your concrete to spoil in the long run. It's not very durable. So that is why GGBS is rarely used most of the time in geopolymer concrete. So talking about the binder type, you can see that the first mix for A increases when you increase the GGBS content in it. So what it means is you need to have a balance of silicon oxide in your binder and calcium oxide also. So silicon, where we have 90% of fly ash and 10%, you can see the strength is just about 23 MPa. And as you increase the content of your calcium oxide, your strength begins to go up because the percentage of calcium oxide in the binder is coming up. So you can see it in virtually all of the literatures that we used. The first one, these are all different mixes, depending on the mix design from different literatures. So you have to strike a balance in your mix. And before you can do this, you must have a detailed understanding of the chemical composition of the binder you are using for your geopolymer concrete. You must know the percentage of calcium oxide in your fly ash or in your slag. You must know the percentage of silicon oxide in your fly ash and in your slag. So that is what will determine the percentage or the ratio which you mix them, because a combination of both is good. If you use GGBS, from the beginning of your mix, you have a higher chance of getting good strength. It accelerates the strength. And in, let's say for precast elements where you have to demold a couple of days after casting, GGBS enables you to attain the desired strength you want before you can demold. So when you use just fly ash, you don't have the chance of getting that early strength. It takes longer to get the strength, like I said. So why is this? Because of the high percentage of GGBS increases the compressive strength in your geopolymer concrete. So a combination of fly ash and GGBS is most suitable aluminosilicate precursor for geopolymer concrete. So if you're using, why I said this is, for now, there is no determined percentage or ratio for GGBS or fly ash in any of the mix, in any of the literatures. So the mix ratio has not been standardized. So it all depends on your desired strength and the desired purpose or application of your structural element. If you need early strength, then you introduce slag at a higher percentage so that your calcium oxide will be a bit high in your concrete. However, if you don't need very high strength, you can reduce the percentage of GGBS and use a higher percentage of fly ash. Then the next thing that affects the compressive strength is the alkaline liquid to the binder content. So like I said, it's lost like the water cement ratio in your normal cement. So if you use a higher alkaline liquid to a binder ratio, you're likely to get a lower strength, because what it means is your binder is less, you have a higher amount of alkaline solution. So the implication of that is geopolymerization will not take place very well. It will not be effective. You have a lot of water. Your mix may have a high workability, but your strength will be very low. And on the other hand, if you use a lower alkaline liquid to binder ratio, you're most likely to get a higher strength, because the binder content is going to be high. Then the alkaline liquid may not be as high as it would if the ratio is much higher, but you're going to get a very good strength, which is also the same for normal concrete. If you use say 0.35 or 0.4, you're in a better position to get a good strength. So most times, like I said, the ratio that is acceptable or recommended for the design of geopolymer is between 0.35 and 0.6. So if you're using 0.7, most times your strength may be too small, may be very, very small. That being said, then another factor that affects the compressive strength is the ratio of the sodium silicate to the sodium hydroxide. And I'm going to take some time to explain this a bit larger. You can see that here, for mix A, it kept going up. When the ratio is one, you have 1%, you have about 37.7 for mix A. So the ratio kept increasing up to a ratio of 2. But when you got to 2.5, you realize that it came down. So what it means is the sodium silicate is now too high, and the sodium hydroxide is very, very small. So what helps your concrete to attain a good strength is, one, the sodium hydroxide content in the geopolymer mix, and secondly, the calcium oxide and the silicon oxide in it. So if you reduce the content of the sodium hydroxide too much, you're not going to get a very high strength, regardless of the binder content that you used. Because the binder content is useless if the chemical composition is not broken down by the hydrates in the sodium hydroxide. So the reaction between the sodium hydroxide and the chemical composition of your binder is what fosters your strength. Then, after it solidifies, you need your sodium silicate to densify your concrete. So the ratio between your sodium silicate and your sodium hydroxide, you have to be able to strike a balance such that the binders in your geopolymer have enough sodium hydroxide to work with to help them give you the strength that you deserve. And the sodium silicate is enough to bond your entire concrete. The geopolymer matrix or the geopolymer paste and your fine aggregate and your coarse aggregate are effectively bonded with the content of your sodium silicate. So most times, there is what they call trial mix in geopolymer concrete. You don't just pick one ratio and you get what you want. You play around with it. But like I said, most times for the trial mix, they use in the ratio of 1.5 to 2.5. You play around that to most times it gives you both a good workability and a good strength. Then the molarity of the sodium hydroxide. If you look at all the mixes, the first mix for mix A, mix B, and mix C. I know I said increase in molarity increases the strength of your GGBS because the sodium hydroxide content, if it's more concentrated, it enables a higher reaction with your binders and a speedy reaction. So you're most likely to get a higher content with a higher concrete with a higher geopolymerization. However, if you go too high, in some cases, when you go past 14 molarity, the strength may reduce. So why do I say that? For mix A, for mix B, for mix C, it keeps going up as you increase the molarity, even up to 16 in some cases. Then mix D and mix E at 14 molarity, you can see that the strength came down. So now there are factors that can affect the reduction in strength at a higher molarity. One of it is the type of the binder you are using and the binder content. So if the calcium oxide is very high in your binder content and you increase and you use a very high molarity for your sodium hydroxide, you realize that the moment you add the alkaline liquids to your mix, because for geopolymer, normally you mix your fine aggregate, your coarse aggregate, and your binders, your alkaline precursors together first before you put the alkaline liquid. When you're producing geopolymer concrete, that is the procedure. So when your molarity is too high, so you realize that the moment you add your alkaline liquid, in less than 5 minutes, your concrete has solidified. Solidified doesn't mean it has a good strength because it will have a lot of pores. You cannot compact it. So that is why you see in this situation, when you go too high, your strength is reduced, not because it didn't set very fast. It set actually too fast to the point that you couldn't compact it. So you're not advised to use a molarity that is too high. You're not advised to use a molarity that is too low. So that is why I said you can play the range of 8 mole and 14 mole, which is quite okay to give the desired strength. So now if you try to summarize the material properties of geopolymer concrete, it's as if workability and compressive strength are inversely proportional to each other. So for the first one, I said increase in alkaline liquids to alkaline precursor leads to increase in workability. If you increase the ratio, you have a higher workability. However, if you increase the ratio, you're going to have a lower compressive strength. Then you go to the molarity. If you increase molarity reduces workability of your geopolymer concrete. Then in the same vein, increase in molarity increases the compressive strength of your geopolymer concrete. Then the second point, increase in the ratio of the sodium silicate ratio reduces workability. Now the inverse is the case, it increases your strength. Then higher percentage of calcium hydroxide in your binders reduces your workability. In the same vein, when you have a higher content of calcium hydroxide, it increases your compressive strength. So if you look at this, you begin to wonder, how can I now design my geopolymer concrete to give me my desired strength properties? Because for, let's say, mass concrete, you can decide to use a low molarity, a low ratio of alkaline liquids to binder ratio, where the strength is not an emphasis. Maybe you need 20 MPa. So you can reduce this and you have a high workability and a strength that is not too high, and you'll be able to do your casting. But take, for instance, you want to cast a structural element. I want to cast a slab, I want to cast a beam, I want to cast a column. I need the concrete must be very workable, very, very workable before I can cast the structural element. That is one. Secondly, is a structural element. It's going to be carrying load. So the strength must be very high. So going by this summary, it looks impossible to achieve that. But like I said, a detailed understanding of the chemical composition and the ratios is what will enable you to be able to carry out your mixed design of geopolymer concrete. So now if you go into mixed design proper of geopolymer concrete, after you have understood how to play around your parameters, we'll now come to the mixed design. For ordinary Portland cement, you have a standardized method of carrying out your concrete mix design. However, for geopolymer, there is no standard method at the moment. So we've got some researchers have proposed methods to use for the design of geopolymer concrete. So I classified it into the first method, the batch one. The density method is the first method by Lloyd. So if you want to know the procedure, you check the journal. You see the processes for carrying out the design of geopolymer concrete there for both the density method and for the volume method. So the density method, I call it density method because it was designed, you design it from the density of concrete. So if you want to design using Lloyd method, normally the density of concrete is 2,400 kilonewton per meter cube. So you pick that 2,400 kilonewton per meter cube, then from there, you now ascertain the percentage of fine aggregate and coarse aggregate that you want for your concrete. So most times, 70%, 78%, depending on what you want. So that method doesn't consider the specific gravity of the materials. It also doesn't consider the volume of what you want to cast. So I'm currently doing my geopolymer concrete in the lab, and I used both of them. So if you use the density method, you're going to have a lot of challenges because it assumed 2,400 kilonewton per meter cube for its design. But in reality, we know that achieving 2,400 as density of concrete, most times it's not achievable. So if you use it for your design, you see that there is quite an unbalance in your mix ratios. Then there's another method, the volume method by Putra. So this method, on the other hand, is just like normal concrete design, where you use the maximum size of your aggregate to determine the water content for your mix. Here you use the volume of concrete to determine the parameters that the concrete will be made of, the constituents of the concrete, your fine aggregate, your coarse aggregate, your binders, and your alkaline solution. And you also use the specific gravity to multiply them, which helps you to know the exact quantity that you will be using for your mix. Now, in the next page, I'm going to show you trials I did with both methods. So the first method, I used the density method by Lloyd et al. So if you look at it, my alkaline activator solution ratio to alkaline precursor, I use 0.35 all through. And my binder content wasn't so high though, but it's supposed to give also a very good strength. Then I'm going to be emphasizing on the slump, the setting time, and the strength. So if you look at the method, all the ratios, all the test results that I used the density method, there is no balance. Now, if you look at the first one, the first mix has the slump of 90 mm. By the way, in my project, I'm casting a column, so I need a very high, I needed a very high workability of more than 150, above 150. So in the course of my trial mix, you see the slump is 90 and the strength is 20 MPa. It's very low. Then when I tried to increase the slump to 150, the strength went down again to 15 MPa, which is also very low. Then at this point, I now tried to increase the strength of the concrete. When I increase the strength to 65 MPa and the fifth mix, you see that the slump dropped to 10. So for the density method, it is either your workability is too high and your strength is very small, or your strength is very high and your workability is very small. So my emphasis here is, it's not the parameters that is wrong, but the method of mix design that I used is what made the output to be this bad. Now, if I take these same parameters I used for batch A for the density method and impute it in batch B, the part that constituted the volume of the concrete and enables me to use the specific gravity of the elements to multiply them, I will still get a very good strength, a strength that is way better than that. Then there is another place I want to lay emphasis on, which is on extra water. Like I said, if you remember when I started, I told you how much time do I have left? Mike, please, when it's maybe 10 minutes remaining, you just notify me.
Yep, that's fine.
Okay. The part, okay, on extra water, like I said earlier, the biggest disadvantage, the biggest problem of geopolymer concrete at the moment is not the mechanical properties. It's the workability and the setting time. Now, if you look at the setting time for all my mix, you see it's quite small compared to normal concrete. And normally, if you go through journals, if you look at the parameters we discussed about the binder content, the ratio of sodium silicate to sodium hydroxide, the molarity and all that. I never discussed about extra water. Now, if you read a lot of other journals, you see almost the same thing. They don't discuss about extra water. Now, it is near almost impossible or 99% impossible to produce geopolymer concrete without extra water. Now, I don't want to believe these literatures, they use the water and they don't include it in the journals. Because in the lab, when you mix it, if you mix your solid part, your fine aggregate, your coarse aggregate, and then the moment you add the alkaline liquid, in less than 5 minutes or 10 minutes, no, even 5 minutes, your concrete is solid. At times, you may not even be able to bring it out of the mixer. So most times, extra water is used. Now, if you check most journals, they recommend not to use more than 15% extra water. 15% of the binder is where you calculate your extra water from. So now, if you look at my work for the first mix, I use 30%, even 35% extra water for the fifth mix. I think that is where I use the highest amount of extra water. 35% extra water. And you can see that the setting time is just 6 minutes. It's just 6 minutes. And the slump is, you can see the first diagram here is that diagram of 35% extra water. Now, this is, even conducting the slump test is difficult because the concrete has already hardened. So now I'm talking about setting time now. Ideally, as an engineer, you now say, okay, let's introduce superplasticizer or retarder, which is what anyone will do to prolong the setting time of the concrete. But most superplasticizers that we have in the market now were designed for ordinary Portland cement. Mind you, we have two types of superplasticizer. We have polycarboxylic-based superplasticizer, and we have naphthalene-based superplasticizer. The polycarboxylic-based superplasticizer is a no-no for geopolymer concrete. It has a high negative effect on geopolymer concrete. So the one that is a bit recommended is naphthalene-based superplasticizer because it's alkaline, and geopolymer is an alkaline concrete. So it promotes the alkalinity of the concrete. So, but my emphasis is also from the recommendation, I think the maximum I saw in my literatures was 2. Most, they use 1, they use 1.2, they use 1.5, and then maximum of 2, but it's even rare. You see the 2 is rare. But for my case, there was even a situation I used up to 6. Up to 6, but it didn't have much effect on the setting time. So my point is, superplasticizers now, the ones we have, maybe except more research is conducted or more superplasticizers are produced specifically for geopolymer. Then we can come out and say, yes, super plasticizer has a positive effect on the casting of geopolymer concrete. But for now, not just what I have read from literatures, I'm talking from experience, what I have done. Super plasticizers have little or no effect on the setting time of a geopolymer concrete. That being said, so normally, I wanted to throw a bit more light on this because in my case, this table you see here, I think I took like 5 months or thereabouts in my trial mix. So what was causing the error was not the mix parameters I used, but the mixing method, the mix design procedure that I used. So it is important that you take note of this mix design procedure. So the one by Lloyd is not too okay, it's not too practical for geopolymer concrete. It's not been stated much in any journal, but I'm just saying this out of experience and the concreting I have done in the laboratory. So now that is that's been said in the material characteristics of geopolymer concrete. Now I'm going to go a bit into the structural part. So the structural part, there's not much to be discussed here. I just want to show you that mechanically or structural performance, geopolymer concrete outperforms normal concrete. Now, the first one I'm talking on is on the bond strength. The bond strength is the bond between the concrete and the reinforcement. So an enhanced adhesive bond between geopolymer concrete and steel reinforcement could reduce the tendency of concrete fracture and reinforcement failure. And it's largely dependent on the molarity of sodium hydroxide in the alkaline activator solution, okay? The binder type and the content that allows for high geopolymerization, improve microstructure of the GPC and enhance GPC reinforcement bond. So now if you look at it, you see that for geopolymer concrete, the one that gave the best or the highest bond strength is 14 mole at an alkaline at a sodium silicate to sodium hydroxide ratio of 2.5. So that's where we had the best strength of about 120 MPa. Then that of normal concrete, the highest of normal concrete is 115. So what this is saying is normally when concrete fails, there is this fracture between the, when a structural element fails, there's the fracture between the concrete and the reinforcement. Now the bond between the concrete and the reinforcement is what we call the bond strength. So now what this implies is that a geopolymer structural element will take a longer, can absorb more stress before failure, before the reinforcement and the concrete split more than normal concrete. That's what it implies. So let's say you use it for a beam. The beam is going to have less deflection compared to normal concrete. Same goes for the slab. So a better way to achieve a high strength, a high bond strength between the concrete and the reinforcement is by increasing the okay, by increasing the molarity, using a high molarity. So for this one, if you're doing a structural element design, and the recommendation here is 14 molarity to enable you to have a good workability, to enable you to have sufficient duration to cast your concrete, and to also have the strength that you desire. So also, if you go to the column aspect, geopolymer concrete outperforms normal concrete in column. So for each mix you see here, they were designed with the same strength, but the geopolymer concrete had higher axial load carrying capacity. So if you look at the first one, even though the strengths are quite close. The concrete strength for the first one is 72.5 and 71.5. But you see that the load-bearing capacity is way high. For that of geopolymer, it increased by 12%. Then another research was conducted by another person. Even the compressive strength for the second batch is higher than that of geopolymer concrete. So for this one, we have one of where the strength is 57.8 for normal concrete, and that of geopolymer is 54.2. The compressive strength of the concrete is higher, but the loading increased. The performance under loading with geopolymer increased higher than that. So now this is just telling us that that axial load can be taken advantage of by increasing the molarity, just like we saw in the beam. So if you're designing any structural element, what I want you to know is that the molarity has to be a bit high. Has to be a bit high. My advice here is normally if you use a molarity that is too high, I said earlier that your setting time is going to be less because the geopolymer reaction is going to be high. So my recommendation from my experience is try to use a molarity that is high, even up to 16, if you can. Even up, for me now, I can even use up to 20 if I want. But it's because I'm a bit conversant with the design and how to play around the parameters. Then in your binder, if possible, use 50-50%, 50 of geopolymer of fly ash and 50 of fly ash of the slag. Because what determines the strength of a concrete, like I said, is the calcium silicate hydrate. So you need high percentage of calcium in your concrete, high percentage of silicate in your concrete, high sodium hydroxide in your concrete. Now, ordinarily, if you mix what I have just said, the setting time of your concrete is going to be very short. Now, that is where extra water comes in. If you add extra water, it reduces the concentration of the sodium hydroxide in the mix. And by doing that, it gives you a longer time to be able to cast your concrete. If you use a low molarity and you use extra water, already, let's say you use 8 mole, already the concentration of the sodium hydroxide in the solution is not too high. And even at that, the setting time may not be enough for you to cast your concrete. So you will still need to add extra water. And then when you add extra water, it will reduce the bonding force of the sodium hydroxide and the binder. So your strength may now become too low. So that is why I recommend, if you want to cast a structural element, just use high molarity, use a binder content that has a good amount of silicon oxide and calcium oxide. Then you try to play around the extra water. The extra water will be able to give you ample time for casting and for compaction, and will still give you the strength that you want. So normally, for the extra water, you can begin from 5%, 5% of the binder content. From there, you increase it little by little. Then most likely, before you get to say 20%, you are guaranteed to get above 35 MPa. From my experience, you're guaranteed to get above 35 MPa, way higher than that actually. But I'm just saying 35, that's the least. It cannot go below that. Then the next challenge in geopolymer concrete is the design. The design of structural elements of geopolymer concrete. Now, this is why we don't see geopolymer concrete everywhere. It's one of the reasons why for normal concrete, it has the standards. There's Eurocode, there's BS code, there's ASTM. We have so many codes that stipulates design standard, design formulas for normal concrete. Now, these formulas were derived from the response of these structural elements to loading, to stress, basically due to the stress-strain behavior of the concrete. So researchers have proven that the stress-strain behavior of geopolymer concrete is not the same as that of normal concrete. Now, if you look at the first graph, normally Portland cement concrete, it has this elastoplastic behavior. The elastic part and the ductile part. However, for geopolymer, you can see that the moment it hits the maximum load, I'm talking about the first diagram here, the moment it hits the maximum load, it falls completely, becomes very brittle. It's not a ductile concrete, it's very rigid. Now, the reason for this is, one, because of the high alkalinity of the concrete. So the alkalinity of the sodium silicate bonds it. It makes the concrete to stick together, and it's very, very strong. So it takes a very long time for it to split. And when it splits, it's not gradual. Like you see the curve, it just goes up, then it falls completely. It retains that strength for a very long period till it cannot retain it anymore, then it collapses completely. Now, the implication of this is most of these codes that were derived from normal concrete behavior don't seem to predict the behavior of geopolymer concrete very well. That's the implication of this behavior. Then one of it is in the beams. It's in the beams. So if you look at the chart I have at the right, this is the shear behavior of a beam from the lab by somebody, Abdallah. So you can see that all the standard code, the person checked with ACI 2019, ACI 2014, FIB, and then JSCE. Now you can see that all of them under-designed the concrete. None of them was able to predict even the shear strength behavior of the beam. Now, this is going to be a problem because you cannot design something as a structural engineer and then you cannot go to sleep. You cannot ascertain if what you've designed can sufficiently carry the load imposed on it. So now the way researchers are proposing rectifying this is by adjusting the factors of safety in the present design code. Some propose either you reduce, depending on what you get, if it underestimates or if it overestimates it, you reduce that factor of safety or you increase the factor of safety to give you something a bit close to the actual behavior or the experimental behavior of that structural element. So like for this one, the first shear strength behavior here is 0.16 by ACI, I think 2019, 0.16. But because it was underestimating the shear strength, he now did a regression analysis, this person, and came up with 0.20. So when you use 0.20 to estimate the shear strength of the geopolymer beam, it gives you something close to the experimental result, something close to a more realistic result. But then this is just his test by Abdallah. It's not being standardized. A lot of people have to use this formula. It has to run through so many regression analyses before it will come to be accepted as a standard. Then same goes for the bending moment. The bending moment capacity of the beam, if you look at it, the experimental work for the first one, we have 56.3 MPa, 87.6, 116.87. If you look at ACI prediction, 99% under predicted the bending moment capacity. So if you compare it, for where we have 56.3 for the experimental, we have 47.57 from ACI. Where we have 87.65, we have 78.08. So the summary of it is, in some cases, not all do, in some cases, these design codes by standard codes at the moment, their prediction is not very regular for geopolymer concrete. So what it means is there's a lot of room for research in geopolymer concrete before geopolymer concrete will become a thing of reality, like we have normal concrete, before it becomes a standard, before it becomes acceptable globally. A lot of work has to be done, especially, like I said, in the workability aspect and in the structural design category. This is another example for column design. Column design also, the current factor of safety by ACI 11, I think, is 0.85. But when you use 0.85 for geopolymer concrete, it still underestimated it. So I think in this case, they proposed reducing it. I can't remember. Virtually all the codes, there are issues in their predictions. So another challenge is every geopolymer concrete has a different performance. I'm trying to summarize the general performance of geopolymer concrete. I can do a mixed design in Malaysia and give you the same mixed design, the same parameters and all that, for you to use in the US. and you get a different strength. Because geopolymer concrete is very, very sensitive. If I cast the column for 5 minutes, if I was able to use same mix parameters, and I take say 8 minutes to cast another column, I can guarantee you that the load carrying capacities of those columns will be different. So 1 minute is a very big it's a very big time in geopolymer concrete. Then another thing is the percentage of the fly ash and the GGBS that you use. If somebody uses 90% fly ash and 10% slag, the behavior of that concrete to both stress and strain is going to be different from the person that uses 50% fly ash and 50% of slag. So these are some of the irregularities in geopolymer concrete. But the bottom line is the mechanical properties is higher than normal concrete. If you do your design properly, you're rest assured of getting a very high strength, both for beam, both for column, both for slab. So before it becomes a standard, a lot of research has to be done. We have to be able to come out and say, okay, if I want a strength of 30 MPa, this is the ratio of alkaline solution I should use. This is the binder content. Within a certain time duration, I will have this strength. I will have this workability, and it will give me what I want. So those are some of the challenges that geopolymer is facing at the moment, which is why it's not being accepted globally or internationally. So that being said, these are some of the references. If you want to study more or read more in geopolymer, it will give you more insight on the parameters to use in the design, as well as the stipulations in the codes and all that. So I think this is where I'm going to be wrapping it up. I don't know if I used too much time.
Oh, that's quite all right. Thank you very much for the presentation. Thanks again to everyone else who was able to join us today. We are past 1 o'clock, so we'll save the Q&A. I see a few have already been typed in, so I'll make sure to get those over to the presenter. If you have any others, please shoot them to me via email, and I will send those along. If any of you happen to be interested in presenting one of these webinars, please email us at vptech@texasce.org for more information. You can also go to our website to find a list of upcoming sessions. We're always available for questions and hope to hear from you soon. Thanks again for your time today and enjoy the rest of your afternoon.